Hello all. In this series we are discussing JEE Main 2024 question papers session 1. So in this session we will be talking about morning shift of 27th January chemistry question paper. Okay. So this was the first question. Two nucleotides are joined together by a linkage known as. This is related to biomolecules, nucleic acids. We know phosphodiester linkage is the one present in nucleic acid. Nucleotides are joined together by phosphodiester linkages. And glycosidic linkage, it is present in polysaccharides. Two monosaccharides are joined together by glycosidic linkage. Disulfide linkages we can see in secondary and tertiary structures of proteins. And peptide linkages are present in proteins. It is connecting the monomers of proteins, amino acids of proteins together. It is an amide linkage also. So here definitely our answer will be option 1. Next one, highest enol content will be shown by. Enol, in general, carbonyls have a tendency to stay in keto form only. And in special cases, it can produce more amount of enols in equilibrium. Right. So in the second option, we can see a chance of. In the second option, we can see a chance of more enol content because its enol will be aromatic. Right. Its enol will be 135 trihydroxybenzene, right, which is aromatic in nature. So highest enol content will be observed among these four in option 2. Now next one, element not showing variable oxidation state is. So they are halogens, and we know among halogens fluorine want to exist in -1 oxidation state. It is the most electronegative element of all. Therefore, it has to always preserve its -1 oxidation state. So this is the oxidation state shown by fluorine in its compounds. So it is not showing variable oxidation state in compound formation. Okay. So all the other one we know they can exist in -1 +1 +3 +5 etc. Fluorine will always exist in -1 in its compounds. So fluorine is the answer. Which of the following is strongest Bronsted base? Bronsted acid definition we know. Bronsted base is proton acceptor bases, and we know amines are proton acceptors. So generally we can call them Bronsted bases. And among these four, we can see that in first one, lone pair is in delocalization with aromatic ring, and in second case there are 2 aromatic rings. So it is also involved in delocalization. In third case, the lone pair itself is involved in aromatic stabilization. So it is the least available lone pair, or it is the least basic of all the four. And in the last case, we can see that it is a static lone pair. It is a localized lone pair, not delocalized. So localized lone pair will be most basic. So it's very direct. 1, 2, 3, they all have delocalized lone pair, and in 4 we have a localized lone pair on nitrogen. So fourth will be the strongest H+ acceptor. Okay, now next one, which of the following electronic configurations would be associated with the highest magnetic moment? Okay, so magnetic moment, it is related to number of unpaired electrons. Root of n into n plus 2 Bohr magneton is the magnetic moment, spin only magnetic moment, And if you refer to first option, we can see 3d7 configuration. Argon is completely filled configuration. That is all electrons are paired. Now among 3d7, these 7 electrons, we can say there are only 3 unpaired electrons, right? In 3d7 configuration, we have 3 unpaired electrons. And in option 2, 3d8, it is 3d8, we have 2 unpaired electrons. And in 3d3, clearly there are 3 unpaired electrons, and in 3d6, we have 4 unpaired electrons. So clearly, more number of unpaired electrons, so more will be the magnetic moment. And if you go to the final value of magnetic moments, 3 will be giving rise to root 15 Bohr magneton. If we apply this formula, 2 unpaired electrons means root 8 Bohr magneton will be the magnetic moment. Again, root 15 Bohr magneton And finally 4 means root of 4 into 4 plus 2, which is root 24 Bohr magneton. Okay, so this is the answer. Fourth is the answer. Now, which of the following has highest acidic or highly acidic hydrogen? So most acidic compound among the following, right? So we have carbonyl compounds in all the 4 options, and we know that alpha hydrogens are acidic. Alpha hydrogen of aldehydes or ketones are acidic, you know, due to minus I or strong electron withdrawing effect of the carbonyl group, right? So here we have alpha hydrogen, there we have alpha hydrogen. So this is another alpha. So these are the acidic hydrogens, and we want, these are the acidic hydrogen, and we want the most acidic among the indicated hydrogens, right? Among the indicated hydrogens. Okay, so all the alpha hydrogens we have highlighted here. Okay, among these, we can say that the last one, this particular hydrogen is the most acidic hydrogen because of 2 carbonyl group besides it, right? So these 2 carbonyl groups, and this particular H is flanked by 2 carbonyl groups. This is a 1,3 diketone. So 1,3 diketones will be the most acidic compound among these. Reason, you know, while comparing acid strength, we will just look at the stability of conjugate bases, right? So just remove the most acidic hydrogen of the compound, get the conjugate base over there, and then look at the stability of conjugate base, right? This is the conjugate base of this 1,3 diketone, and you know this negative charge is highly stabilized due to 2 minus R groups present on either side, right? So that is the most stabilized conjugate base. So option 4 will be the most acidic compound, right? So among all these 4 compounds, the most acidic hydrogen will be present in option 4, and that is this particular hydrogen also, due to this stabilized, right? Due to this stabilized conjugate base, right? So 4th was the answer here. Now, from solutions chapter, a solution of 2 miscible liquids, okay, showing negative deviation from Raoult's law will have. We know definition of negative deviation is that a solution, a liquid solution that show less than expected vapor pressure, right? So the vapor pressure predicted by Raoult's law is there, and if the solution shows less than that value, then that will be a negative deviation case, right? So we can cancel both the first and second options because they talk about increased vapor pressure. No, in negative deviation we have decrease in vapor pressure. So this and that will be true, decreased vapor pressure. And you know that if the solution have lower vapor pressure, then it will be boil at a higher temperature only. As the vapor pressure of a liquid decreases, boiling point will increase, right? So the last one is the most correct answer. Option 4 we can choose here. Consider following complex ions. FeF6 3 minus. Okay, 3 complexes P, Q, R and R are given. Arrange them in the order of spinoli magnetic moment. Okay, so for spinoli magnetic moment, we again need number of unpaired electrons in the complex. FeF6 3 minus, you know, ion is in plus 3 oxidation state. Here vanadium is in plus 2 oxidation state. Here Fe is again in plus 2 oxidation state, right? So plus 3 we know it is a D5 configuration. V plus 2 vanadium plus 2 means 3D3 configuration it is. And Fe plus 2 will be 3D6 configuration. And you know in all the cases the ligands are weak field ligands. Fluoride, H2O, these are weak field ligands. So no pairing occurs. So we can simply follow their ground state arrangement itself to predict spinoli magnetic moment, right? Okay. Or you can consider T2G EG separation also. Then also we no need to do pairing there, right? 3D5 means like in ground state, 3D5 here means there are 5 unpaired electrons. In other words, more correctly, if you see the configuration, T2G3EG2 will be the configuration, right? 5 unpaired electrons. 3D3, 3 unpaired electrons, no doubt. 3 unpaired electrons. and 3d6 means there will be 4 unpaired electrons, right? So if you write the configurations correctly, T2G 3Eg0 will be for second compound, and for complex R, T2G4 Eg2 will be the configuration, right? So that is the arrangement. Now clearly P has the highest magnetic moment because it has the highest number of unpaired electrons. If you calculate the spinoli magnetic moment or using the root of n into n plus 2 equation, we can say first case root 35 Bohr magneton will be the value. Second case root of 15 Bohr magneton, and third case root 24 Bohr magneton. These are the values. So we can say P has highest, then R, then Q. So the right choice will be PRQ, option 3. Right. Now, another question was from chemical bonding, choose the polar molecule from the following. So only one has a non-zero dipole moment here, and we know CCl4, it has perfect tetrahedral geometry, so all the bond dipole moments will be cancelling each other, so net dipole moment will be 0. In carbon dioxide, it is linear geometry with 180-degree bond angle, so all the 2 bond dipoles will cancel each other and effective dipole moment will be 0 again, non-polar. CH2, you know, this is also having 0 dipole moment because of symmetry of the geometry. So this is also giving 0 dipole moment, non-polar molecule it is. And in CHCl3, there the bond dipoles are not exactly cancelling each other, and we will have a non-zero effective dipole moment, right? Mu net not equal to 0, but it is very low only. Okay, CHCl3 is the non-polar, so CHCl3 is the polar molecule out of the 1, 2, 3 compounds are all non-polar due to effective 0 dipole moment, right? Now next one, 70th. 4f and 5f series of elements are placed separately, we know, in periodic table to preserve the principle of classification. Yes, to preserve principle of classification and to have a perfect arrangement of elements, right? For 2 purposes are there. They are arranging 4f and 5f series of elements separately to maintain the structure, overall structure of the periodic table, as well as to maintain or preserve principle of classification, right? So statement 1 is very correct statement, it is true. And statement 2, S block elements can be found in pure form in nature. No, S block elements are very reactive metals, so they are not found in pure form at all. So they are always found in compounds only, and statement 2 will therefore be false, right? They are never found in pure form. So first is true, second is false. Option 3 we can pick. 1 is true, 2 is false. Next one again, statement 1, statement 2 type. Paranitrophenol is more acidic than metanitrophenol and orthonitrophenol. That is correct. Paranitrophenol, if we arrange them in the increasing order of acidity, paranitrophenol will be most acidic among nitrophenols, then orthonitrophenol, and the least acidic will be metanitrophenol. So first statement is very correct. Para is more acidic than both ortho and meta isomers. So this is true statement. Now statement 2, ethanol will give immediate turbidity with Lucas reagent. No, ethanol is a primary alcohol. Primary alcohol, either no reaction or very slow reaction is the observation, right? So it's very difficult to have a reaction of ethanol with HCl, right? So this is a false statement, will not give immediate turbidity, right? We know ethanol or primary alcohols in general, other than benzyl alcohol and allyl alcohol, they will not give immediate turbidity. They will not give turbidity also. Or in other words, if they want to give a turbidity, we will have to wait a lot, right? So primary alcohol will give is a wrong statement. First is a true statement. Second is a false statement. So we can pick option 1, right? 1 is true, 2 is false. Now, ascending order of acidity of following phenols or alcohols. Okay, so butanol is given, then all phenols. So we know clearly alcohols will be far less acidic than phenols. And among these phenols, phenol having 2 electron withdrawing group will be most acidic. So E will be most acidic due to presence of 2 electron withdrawing nitro groups. And now we have 1 nitro group in case of B. So B will be the next or second most acidic compound. And after that phenol we will pick, because after that, right, after that phenol we will pick, and among phenols the least acidic compound will be C, because you can see a plus R group present in case of C, right? So this plus R donation will destabilize the phenoxide ion, therefore lowers acidity of a phenol. Okay, remember, if it is present at para position, then only this effect is observed. If it is present at meta position, then this will slightly enhance acidity of phenol, right, due to electron withdrawing nature, minus I nature. Okay, so anyway, option C, this compound C is para methoxyphenol, and para position methoxy group will show plus R effect, therefore lowers acidity of phenol, right? Electron donating groups lowers acidity of a compound, right? So the correct choice will be EBDCA. Okay, option 4 will be the correct choice. Next question from P block, group 13. Melting point of boron, while is also given, is initially high in group 13 elements. Yes, that is true. Boron has greater than 2000 Kelvin melting point. That is true statement. And reason is given as solid boron has very strong crystalline lattice. Yes, that is also true and explains assertion also. So the reason for initially high melting point of group boron among group 13 elements is due to the strong crystalline lattice of boron, right? So that is very direct question, and so we can pick answer option 2. You know, if you refer to the melting point of other group 13 elements, they are far less than 2000 Kelvin. So they are below 1000 Kelvin also. So our option will be answer will be option 2 here. Next question, cyclohexene is which type of an organic compound? Cyclohexene, you know, this is a cyclic and aliphatic compound, right? So if it is aliphatic and cyclic, we will call it alicyclic compound. It is alicyclic organic compound. If there were 3 pi bonds, then that will be aromatic, benzenoid aromatic type. But this is not aromatic. This is just an unsaturated cyclic compound. We'll call alicyclic compound. Yellow compound of lead chromate gets dissolved on treatment with NaOH solution, hot solution. The product of lead formed is, okay, we know if we take lead chromate PbCrO4 and add NaOH, then such a complex anion is formed. PbOH4 2 minus is formed. So if you write the correct formula, complete formula of the compound, we will write Na2PbOH4. Right. So sodium tetrahydroxide of plumbate 2 is the IUPAC name of that compound. Here we have to choose the correct option. So that is clearly a dianionic complex, 2 negative charges. Therefore, dianionic it is, and coordination number is 4. Coordination number is 4, right? So option 4 will be the correct choice. So PbOH for 2 minus is formed, which is dianionic, and coordination number 4 compound. Right. Now aqueous solution of ammonium carbonate is basic. Yes, ammonium carbonate is a base, therefore its solution will be basic, we know. And statement 2 says acidic basic nature of salt solution of a salt of weak acid, weak base depends on Ka and Kb value of the acid and base forming it. It is also correct. We know pH of salts, if you refer, pH of salt of a solution of salt of weak acid and weak base, we have the final derived formula 7 plus half into pKa, 7 plus half into pKa minus pKb, right? So this is the final formula. Clearly Ka and Kb are present within this equation. So pH is dependent on Ka, Kb values of the acid base components of the salt. Here our salt is ammonium carbonate. Ammonium carbonate. Ammonium carbonate, you know, it is formed from weak base ammonia and weak acid carbonic acid. Ammonia's pKb, you know, it is close to 4.75, and H2CO3's pK values, if you refer, pK1 is 6.3 and pK2. Two hydrogens are acidic here. pK2 is 10.3, close to 10.3. Okay, so clearly the difference between pK and pKb in this case is going to be greater than 0, right? pK is higher than pKb. So definitely the final pH of the solution will be greater than 7, right? It is going to be basic solution. So both statements are correct. Both are correct statements. So we can pick option 1 here. Both are correct statements. The IUPAC name of following compound is, so we have a cyclic compound and branched also. We have 2 methyl branches on this carbon and 1 ethyl branch on this carbon. So we'll start numbering from here only because that carbon has more number of branches. Okay. So the mostly branched, the highly branched carbon should get the lowest number. That is the rule. So that is the way we number the carbon chain. So it is going to be 3-ethyl according to alphabetics. We'll call it 3-ethyl 1,1-dimethyl cyclohexane, right? So 3-ethyl 1,1-dimethyl cyclohexane, option 2 will be the correct one. So while numbering, we have to look at the amount of branching at each carbon, and while naming it, we have to look at alphabetics also, E first, M second, right? NaCl reacts with constant H2SO4 and potassium dichromate to give reddish fumes of B, which then reacts with NaOH to give yellow solution C. Identify B and C. Okay, this is Chromyl chloride test, isn't it? This is Chromyl chloride test for chlorides. So that is a confirmatory test for chloride anion. If you take NaCl or a chloride containing solution and treat it with potassium dichromate in presence of concentrated sulfuric acid, we'll get Chromyl chloride, which is reddish brown fumes. So CrO2, Cl2 is formed. So that is going to be our B, compound B. And along with Chromyl chloride, you know, NaHSO4 and KHSO4 also are formed. Okay. So B, we identified B, Chromyl chloride it is. So we can see Chromyl chloride in 3 options. Now C, we need to identify which reacts with NaOH to give yellow solution, right? So Chromyl chloride, if you treat it with NaOH solution, then you know it is forming sodium chromate, which is yellow solution. This is soluble compound, so we'll see yellow solution. That was a gas, colored gas. So sodium chromate is the compound C, not dichromate. So option 1 will be the correct answer here. The correct statement regarding nucleophilic saturation reaction in a chiral alkyl halide is, okay, nucleophilic saturation SN1, SN2, they are talking about. In SN1, you know, racemization is occurring, and in SN2, you know, the inversion of configuration is occurring, right? So answer is option 4. Okay, 4 is the answer. The electronic configuration of neodymium, atomic number is also given. We know it is a lanthanoid, cerium, praseodymium, neodymium. Its electronic configuration is going to be F4 type, right? It is the third lanthanoid, therefore its electronic configuration is going to be F4, 4F4, 4F4. That is 6s to 4F4, option 1. Next, the integer section questions. The mass of silver displaced by a quantity of electricity which displaces 5600 ml of oxygen at STP will be. Okay. We know equivalence of silver displaced will be equal to equivalence of oxygen displaced, right? This is the rule or law. So equivalence of Ag displaced will be equal to equivalence of oxygen displaced. Equivalence of Ag we can write, we need mass of silver, so mass of silver divided by equivalent mass we can write, equivalent mass of silver. And there equivalence of oxygen we need to write. So from this we are directly getting number of moles of oxygen, right? 5600 ml O2 at STP means 5.6 liter oxygen at STP. 5.6 liter means 5.6 divided by 22.4, which is for 1 mole. So this will be 1 by 4 moles of O2, right? So this is 1 by 4 moles of O2. So we know the amount of oxygen, number of moles of oxygen. And on right hand side we can substitute it this way, moles of O2 into N factor, right? So this is the equation in the working formula. And mass of Ag by equivalent mass, we need to find mass of Ag. This is the question. Mass of Ag displaced. Equivalent mass of Ag is given. We know N factor of silver is 1 because Ag plus we are taking, we are preparing Ag, and there we require 1 mole of electron, right? So N factor is 1. N factor for Ag is 1. And for oxygen, we are taking H2O to release oxygen gas. And for oxygen, you know, here -2 is the oxidation state, and we have 2 such oxygen atoms. So overall -4 is the oxidation state on LHS, and there are 2 oxygens in 0 state. So we will be requiring loss of 4 electron from 2 H2O to form 1 mole of O2, right? 1 O2. So that means N factor is 4 for the oxygen's case, right? So per mole of oxygen formed, we require 4 electron supply, 4 mole electron supply. Per mole of Ag formed, we require 1 mole of electron transfer, right? So that is why N factor is 1 there for here. So using that logic, equivalent mass of Ag we can say it is molar mass itself, molar mass divided by 1 it is. So mass of Ag divided by equivalent mass is 108 grams, and moles of O2 formed is 1 by 4 mole, and N factor we found it is 4, right? Which says that mass of H is going to be 108 gram. So by the quantity which releases this much of O2 at STP, we'll be able to release 108 gram of silver metal, right? So our answer will be 108. Consider the following data for reaction HI giving H2 plus I2. Data is given. Concentration of HI has been given. Rate of reaction for each case is given. Order of the reaction is, for this equation we know rate is equal to some constant into concentration of reactant, which is only HI raised to some value N. Okay. So it is the rate law for this reaction. Now, if you refer to the table, HI's concentration, initially they have taken 0.005 molar and then they have rise to 0.01, which is doubling, right? And then again they have doubled the initial concentration of HI, and then the corresponding rates, if you refer, first case 7.5 10 raised to minus 4, as we doubled the HI concentration, a quadrupling of rate is observed, right? This is 4 times of previous rate, and again doubling means again doubling the initial concentration of HI, the initial rate again quadrupled, right? So doubling of initial concentration of HI causes quadrupling of the rate, which means order must be 2, right? So order of this reaction will be 2 only. If we double the initial concentration, then if the rate is also doubled, then the rate order of reaction will be 1, right? Here it is squaring effect, therefore 2 is the order of reaction. Okay, so it was a simple one. Now, next one, mass of methane required to produce 22 gram CO2 after complete combustion is, okay? We know if we take methane 16 grams, 1 mole. From it we can produce, by complete combustion, we can produce 1 mole of CO2, right? From 1 CH4, 1 CO2 can be produced, which is 44 grams CO2. Question is about, if we want to prepare 22 grams CO2, how much CH4 must be taken? Okay, if we want to prepare 22 gram, then we must take only 8 gram, right? 8 gram of methane will be required. So 16 gram will give 44 gram CO2, therefore 8 gram will give 22 gram CO2. Simple stoichiometry related question. 8 is the answer. From thermodynamics, if 3 moles of an ideal gas at 300 Kelvin expand isothermally from 30 to 45 decimeter cube against a constant opposing pressure of 80 kilopascal, then amount of heat transferred is. We know isothermal expansion it is, and for isothermal expansion of ideal gases, first law says Q plus W will be equal to 0. Delta U will be equal to 0 for isothermal expansion of a gas, ideal gas. So Q plus W is going to be 0. If we calculate W, just a negative of W will be Q, right? So W, we know its equation for irreversible process. This is an irreversible process because it is against constant external pressure. So work done in irreversible isothermal process, we can write minus P external into delta V, right? V final minus V initial. So that is minus 80 kilopascal means 80 into 10 raised to 3 Pascal into V final is 45 and V initial is 30 decimeter cube. So this is 15 decimeter cube, and 15 decimeter cube will be 50 into 10 raised to 15 into 10 raised to minus 3 meter cube, right? We want final answer in joules, which is the SI unit of energy. So we will put all the terms in SI units only, Pascal and meter cube. Okay, we know 1 Pascal meter cube is called joule. And if you calculate this value, then minus 1200 joule will be your answer, W, and Q will be reverse of that, 1200 joule. So amount of heat transferred in joules will be 1200. Okay, next one, 3-methyl hex 2-enol reaction with HBr in presence of peroxide forms addition product. Okay, number of possible stereoisomers for A is. Okay, let's identify the correct product first. This is some anti-Markovnikov addition, you know, peroxide effect or Karaj effect. So let's write the formula of starting compound. It is a hexene, hex 2-ene with the methyl group on third carbon. So this is the starting compound and we are doing HBr plus peroxide reaction. Right. So that is an anti-Mark addition. Therefore, the final compound will be of this form. Structure will be this one, and here you can see two stereocenters. This is an asymmetric carbon, chiral carbon. This is also a chiral carbon. So two chiral carbons we can see here, and stereoisomers here means optical isomers, right? Geometrical isomer is not possible here. Optical isomers we are referring to, and total number of stereoisomers for n stereocenters will be, if we have n stereocenters, so this formula is applicable for geometrical isomers also. So in general, if there are n stereocenters, 2 raised to n stereoisomers will be possible. This equation is applicable exactly when the molecule is not symmetric, right? The molecule is not symmetric here. We cannot divide it into equal halves, right? So this formula is applicable here. So 2 raised to 2 will be the answer here. 2 stereocenters. So 2 raised to 2, which is 4 stereoisomers. This compound can have. Among the given organic compounds, the total number of aromatic compounds is, first one is clearly non-aromatic because we can see sp3 carbons in between. So there is no complete delocalization possibility. And in second case, you know, this ring is aromatic. So this is an aromatic compound. And third case, you can see there are 10 pi electrons. Right, 10 pi electrons, 1 pair, 2, then 3, 4, 5. 5 pairs of pi electrons, meaning 10 pi electrons, which fits into the formula 4 into 2 plus 2. 4n plus 2 formula is applicable here, right? So this is also aromatic, complete conjugation is possible. And after that, in last case, here we can see, right. In the last case, if you redraw the diagram, draw the other resonance structure, then it is very clear that there is complete delocalization possible and there is complete delocalization is possible throughout the system, and the number of electrons involved in delocalization is 3 plus 3 plus 1. So 7 pairs are there, meaning 14 pi electrons, right? Here we have 14 pi electrons, which again fits in the formula 4n plus 2. 4 into 3 plus 2 it is, right? So Haeckel's rule is followed here also. So it is also aromatic compound. So B, C, D are aromatic compounds. So the answer is 3. 3 are aromatic. Among the following, total number of meta-directing functional groups is. Okay, meta-directing functional groups. First one, it is orthopara-directing. Second one is a meta-directing. Nitro group, minus I minus R group, no plus R effect. Minus I minus R group, no plus R effect. This is also minus I minus R group, so it is also meta-directing group. This has plus hyperconjugation and plus I effect, so it is orthopara-directing. NHCO3, we have lone pair on nitrogen, which acts as plus R group, so it is orthopara-directing. COR, it is a minus I minus R group, no plus R effect, so it is a meta-directing group. OH, clearly it is a orthopara directing group. COOH, it has minus I minus R effect, so meta directing it is. Chlorine has plus R effect, so it is orthopara directing. So 1, 2, 3, 4. 4 are meta directing function groups in electrophilic aromatic substitution reaction. Answer is 4. Number of electrons present in all the completely filled subshells having n equals 4 and s is equal to half plus half is right. N equals 4 means fourth shell, and fourth shell, you know, it has 16 orbitals. 16, 4 square orbitals. Which are those? 4s, 4p, 4d, 4f. These are the orbitals. 16 orbitals are there. In each orbital, we can have a electron with plus half spin direction. Right. So there is maximum of 16 electrons with this particular combination of quantum numbers. Right. So answer will be 16. Sum of bond order of CO and NO plus is carbon monoxide, it is having bond order 3, and NO plus, it is also having bond order 3. Right. So 3 plus 3 is our answer, which is 6. So just draw the Lewis structure. So it's very evident that 3 and 3 are the bond orders, or in other words, if you get bond order of 1, then we can say bond order of other also, because they are isoelectronic species. So isoelectronics have same bond order, so 3 plus 3 is 6. From the given list, number of compounds with plus 4 oxidation state of sulfur is, in SO3 we have plus 6 oxidation state, in H2SO3 we have plus 4 oxidation state, SOCl2 we have plus 4 oxidation state, SF4 again plus 4 because fluorine is minus 1, barium sulfate we have plus 6, it is sulfate anion, and H2S2O7 oleum, it is again plus 6 oxidation state. So we will find 3 compounds in which sulfur is in plus 4 oxidation state. So that is the end of the question paper. Thank you all.